Hi everyone, my name is Gabinan and I'm a PhD student at KAIST in South Korea. Today I'll be presenting our paper titled FTG, a precise measurement of fault diagnosability gain of test cases. Now, what do I mean by fault diagnosability? Fault diagnosability refers to the ability of a test suite to effectively locate faults once errors are observed. For example, let's imagine that a test suite has this coverage pattern where every test case covers every function in the target program. Assume that function 5 contains a fault that makes all 3 test cases fail. In this case, even though this test suite can detect the fault, it cannot really pinpoint the faulty location. For example, if we apply SPFL, such as OCI, to this coverage matrix, all 5 functions will be assigned the same score. When the coverage pattern of a test suite provides little information about the faulty location, we say that the test suite has low fault diagnosability. Now let's look at another test suite. As in the previous example, function 5 is faulty, which makes test 1 fail. Here, we can easily see that function 5 is the only suspect for the buggy location. SPFL will also give the highest score to function 5. Like this, if we can accurately find the faulty location using the test coverage, we can say that the test suite has high fault diagnosability. As we've seen, even for the same faulty location and with the same SPFL technique, the accuracy of fault diagnosis can greatly vary depending on the test suite. Then, what causes the difference we've just observed? One of the most important factors that affect fault diagnosability is the ambiguity groups in the coverage matrix. An ambiguity group is a set of program elements that are covered by the exactly same set of test cases. Therefore, if a faulty element belongs to a large ambiguity group, then the SPFL will inherently be less accurate because it is hard to distinguish the faulty element from the many non-faulty elements. On the other hand, if a faulty element belongs to a small ambiguity group, it is much easier to accurately locate the faulty elements. Now, suppose we want to improve the diagnosability of the test suite by adding a new test case. Among the 3 test cases on the slide, new test 1 increases the FL accuracy by the most, while adding new test 3 does not have any impact on the accuracy at all. In such a case, new test 1 brings the highest fault diagnosability gain to the test suite. Then the question is, can we quantify the fault diagnosability gain introduced by a new test case? Suppose that we have a measure F that takes the current test suite and the new test case as inputs and estimates the fault diagnosability gain. Then, such a measure can be used to efficiently augment an insufficient test suite. There are actually several existing metrics designed to capture such information gain. Most of them have been proposed as part of test prioritization techniques for better FL. Moreover, a measure that can quantify the diagnosability of a full test suite can also compute the information gain of a single test case. Simply the difference between the fault diagnosability of the new and the original test suites. There are several diagnosability metrics for test suites, such as DDU or TFD. In our work, we classify those measures into 2 categories based on the information used. The first category is the result agnostic measures that only use the coverage of the test cases. The second is the result aware measures that take into account the result of the existing test cases as well. Then, if the failure is already observed, which categories measures can increase the FL accuracy faster? To answer the question, we evaluate the existing diagnosability gain measures using the defect4j fault data set shown in the left side. Each faulty subject in defect4j has its own test suite where at least one of the test cases is failing. For each faulty subject, we first set the initial test suite for FL to contain only one failing test case from the original test suite. Then, the test case whose estimated diagnosability gain is greatest is iteratively added to the test suite. This graph shows how the FL accuracy changes as a new test case is selected by each measure. The results show that the two result-aware measures, F3 and probes, outperform all result-agnostic measures. This demonstrates that using test results as well as the coverage is useful as long as test results are available. Then why is this so? It is because test results can give info about which parts of the program are related to the fault. Indeed, both of the best performing measures, F3 and probes, focus on the information from failing test cases. For example, F3 prioritizes test cases that can more evenly split higher priority ambiguity groups, where the priority of an ambiguity group is defined as the number of failing test cases covering the group. The other measure, probes, prioritizes test cases that have similar coverage with the current failing test cases. However, we noticed that existing measures do underutilize the information from existing testing test cases. Testing test cases can show us which parts of the program are less important in terms of localizing the fault. Based on this idea, we propose new fault diagnosability gain measures that utilize the ongoing FL results, which summarize information from both failing and passing test cases. We suggest two novel diagnosability gain measures, split and cover. Split is designed to break more suspicious ambiguity groups, while cover is designed to focus on covering more suspicious elements. They can be also thought of as the generalized and normalized versions of F3 and probes, respectively. Our empirical evaluation shows that split outperforms F3 and cover outperforms probes in terms of the FL accuracy improvement. Finally, we suggest a unified fault diagnosability gain metric, FDG, combining our novel measures, split and cover. It is defined as the weighted sum of both values, with one hyperparameter alpha determining the relative weights of both measures. We evaluated FDG using the same dataset as before, and the results show that FDG significantly outperforms all 9 existing measures that we studied in the paper. Now that we know FDG can precisely measure diagnosability gain, the next natural question is whether FDG can help augment a test suite for FL. When a test suite is insufficient to diagnose the observed failure, we may generate new test cases and pick only the useful ones using FDG. In our paper, we call this scenario iterative fault localization, and I'll describe it in more detail step by step. First, suppose that a test suite is not enough to accurately localize the fault. Then, we generate new test cases for the program using an automated test generation tool such as EvoSuite. Here, note that the generated test cases just capture the current semantics of the target faulty program. Then, among the generated test cases, we use FTG to select the test case that is predicted to yield the highest fault diagnosability gain. Next, a developer acts as the oracle of the selected test case. Here, the oracle judges whether the test case exposes the faulty behavior of the target program or not. For example, let's look at this test case generated for Math 59 in Defect4J. This test case reveals the faulty behavior of the target program as a human found the assertion incorrect and therefore is labeled as failing. We repeat this test selection and labeling process until the querying budget is exhausted. Finally, the newly labeled test cases are added to the test suite. We simulated this iterative FL scenario using Defect4J. We set the initial test suite to contain only the original failing test case for each Defect4J fault and checked how much the generated test cases selected by FTG increased the FL accuracy. For test generation, we ran EvoSuite for 10 minutes, and human labeling was simulated using the correct version of the program. This bar graph shows that the FL accuracy increases as more oracle queries are made. Even when only one test case is labeled and added to the test suite, accuracy at 1 increased approximately by 5-fold, while adding 10 test cases improved accuracy at 1 by an order of magnitude. The next research question concerns the robustness of the scenario. During our scenario, human can mislabel the test cases, and those labeling errors can degrade the FL performance. But by how much? Our results show that despite some errors in labeling, especially up to the error rate of 30%, adding new test cases still increases the FL accuracy compared to the initial test suite. This is because correctly labeled subsequent test cases can mitigate the impact of earlier labeling errors. Finally, we conducted an experiment to find the ideal value of the hyperparameter alpha. Please note that in all previous evaluations, we used a default value of 0.5. This table shows the performance of FTG with different alpha values in terms of the FL performance of the augmented test suites. The results show that higher alpha values, which put more emphasis on split, tend to produce better performance. Although alpha needs to be tuned when used in practice, these results show that FTG can outperform the best performing existing metrics even with the default setting. Okay, let me finish the talk by summarizing our paper. In this work, we analyzed the existing fault diagnosability gain measures and proposed our novel measure FTG based on the insights from the analysis. The empirical evaluation with SPFL shows that FTG can more precisely measure the diagnosability gain of test cases than existing measures. We also introduced an iterative fault localization scenario and show that insufficient test suites can be efficiently augmented using FTG to prioritize automatically generated test cases. Thank you for listening.